Welcome to this Sahara 4 exercise. In this exercise, we will discuss about the water injection pattern simulator, and the idea is to, in this exercise and in the following exercise, we will prepare the simulator and run some simulations to adjust the historical data and then create a forecast of the secondary recovery of the project we have been working with. So in this case, for this exercise, we won't do any specific calculation or any work in Sahara on its own, but what we will do is talk about the pattern simulator and how it works. So the minimum unit of calculation that we have available in Sahara is called the flow element. This will connect a producer and an injector, and is going to represent the reservoir volume in which the sweep from the injector to the producer occurs. An injection grid is composed of the flow elements that connect an injector well and with the neighboring producers in each of the layers where they are present. So it's completely vital that we understand what is a flow element. The flow element is going to represent the connection between an injector and a producer, and is going to be defined by the shape it has, the area. Also, is going to be defined from which injector to which producer is connecting. It will also be necessary to understand which is the pore volume inside that flow element, and also which is the saturation of oil inside of it. And we need to understand that each flow element will be defined for a different layer. You can create flow elements at the well level, but they don't have much significance in the sense of using the simulator. Normally you will want to create a lot of different flow elements that will be defined for each layer, and also they will be dynamic over time. If we open or close injectors or producers, we need to update this information and have the flow elements be changing over time to reflect these changes as well. So then we need to understand that we will have flow elements for each layer, and we will have flow elements for each date, and also for each well and each producer. Each flow element will have then a pore volume that we need to have defined, and also a saturation that will change over time as the sweep of water across the flow element occurs. In general, the simulator will have 5 different methods that we can use. 3 of them are analytical. The 3 are the segregated flow equations, the Buckley and Leverett equation, and the Craig, Geffen, and Morse equations. Also, we have 2 empirical models that will be the characteristic curve that will connect directly the amount of MOPS, that means the amount of pore volume normalized by the mobile pore volume of water injected to oil produced. So it's going to make a direct connection between both of them, and it's going to completely explain the change of the the oil saturation over time in the flow element and the amount of oil that is produced in the producers coming from here. The other empirical model will be the WAR. In this case, we'll create a connection between the WAR and MP curve, and is going to use some empirical constants to do the connection from the water injected to the produced oil. We will see them in more detail in a future exercise, but having consideration that we have these 5 methods available, 3 of them analytical and 2 of them empirical. The flow element, as we discussed, is where all these equations will be applied, and we will need to characterize it by this pore volume. The minimum data is always the pore volume, the initial and residual oil saturation, and the petrophysical parameters that will be required by the calculation model that we use. And in this last point will change obviously from one to the other. For example, in characteristic curve, we will not need as much data associated to the wells as with the other models that will use more information. For example, the Corey exponents that will be used for Buckley and Leverett, for example. So all these calculation models will finally allow to calculate the fraction of water as a function of the accumulated water injection. So we need to have in consideration that always the methods will do the connection between how much water is being injected and how much oil is being extracted from the sweep of water. The different methods will not say anything about the water produced, like the total liquid produced. That is going to come from the coefficients that will be associated to the each different flow element. And again, we will discuss it in more detail in the future. This is just like a general review before we start. Um, so if we something that we need to do this calculation is understanding how much monthly injection we have in each layer. So that probably is one of the most important unknown is how the distribution of that layer injection is also in the aerial sense, because we need to understand how much water is going in each layer, but also how much water is going to each producer. We have a number of different methods that we can use to initialize these coefficients that will create this distribution between the different producers connected to the injector in with the flow elements in a specific layer. So in general, the work methodology that we want to use for this simulator is initially you're going to assign injection aerial distribution coefficients to the different different flow elements, and then you will want to using these coefficients achieve an historical adjustment that is good enough of the oil and water production curves by modifying them. So you are going to iterate and do a first approach of this, initialize these coefficients at first, then you will calculate your total liquid rate and your oil rate, see if it makes sense with the method that you are using and the coefficients that you define, and then you will start adjusting the coefficients over and over until you have a good match with the history data. So to perform the simulation of a water injection project, we are always going to recommend to perform some previous reviews in order to validate the input. Your model will be as good as the input data that you put them. So just some recommendations, some steps to follow before starting with the simulation. So first, verify that there are all active producer injectors in the project. So verify that your wells have the correct status of the offset, that the wells currently update from producers to injectors when you do conversion, that they are actually have the offset status correctly defined. Also verify the status of the layers if they are correctly open or closed before starting. Always check that the map reflects this precisely. We can see here in this project that we have the status of the here we go into objects symbols simulator. We can see over time that we have the changes in injection and producers. For example, if I plot here my let's do a new plot, and I will do a very basic plot here with the y-axis, monthly history, oil object total, liquid object total, and injected water object total. Here I will change the colors, oil in green, liquid in black, and injected water in this magenta color, something more like this. So here we can see that if we check on the date, chart, go to date, here. So we can see here that this well is currently active from this point onwards, so this is okay. We see the status of the object is correct, and also we can see that over time it's still open, and here we have the change from producer to injector. But always, if you have you should have your at least your injection per layer. Check if the information there is correct, that all the all the all the injection that you have per layer is correctly tied to the layers that are open in each different date. So you should check it with these different options as well. In this case, I just plotted for the well level, but if you should have injection per layer, and you have to check that as well to see if the status are changing accordingly to the production information that you have. Also check that the accumulated production for the history scenario are correct. That is important because we want to check the scenario. The history scenario is going to be our point of comparison, so all the accumulated productions should be correct based on the information that we have for the field. Then if you want to consider primary production before the like included in the forecast as well, make sure to perform the analysis for the desired wells and save the results in the primary simulation scenario. Remember that all the projects in Sahara have this scenario here. This scenario is intended to be used to save the primary production declines of the wells. Then you will be able to consider them for the forecast of the scenario. Then remember to review the injection history and the injection placement in the layers, like we did with when we check the allocation factors. Have all your allocation factor check. Try to always have all the sum of the allocation factors be 1 in all the cases that you have available. So that's important as well. Validate all your maps as well, because some of them will be used for some petrophysical data. We may need to use the maps, so always check that your maps make sense, that they are correct. We have done some validation of some of the maps in a previous exercise. We validated some porosity data, so that is relevant as well. If we need to import petrophysical data, also check that that is correct. Maybe it is better sometimes to just plot some of the petrophysical data's maps to check if the values make sense. Um, Another thing that is relevant is to always check that you have at least the minimum data that you need for the method that you will use. For example, you will need to have your water saturation at the start of the secondary recovery. Think about how you want to calculate this. We have several tools in Sahara to calculate them, that we will review also in future exercises. But having consideration that you will need to have an idea of what is the water saturation at the start of the secondary recovery. Also, if you have gas saturation at the beginning of the secondary recovery, that is important as well. You have to consider that. Understand your residual oil saturation. Have as well which is your CONAT water saturation, which is the initial water saturation of the project. Which are the all the initial saturations. Those are important as well, because we will need them to understand, to do some of the calculation as well for the initial water saturation at the secondary recovery. Also have at a minimum the oil and water volume factor, the gas factor as well, if you have gas present in your reservoir. The Obviously, if you have gas and it's an important amount of gas that you want to calculate as well, have the total dissolved gas inside the reservoir as well, have that number in mind. um, some other models will need more equations. For example, if for Buckley leverage you will need the Corey the the Corey exponents, so you will need to have that information as well. You will need to have an understanding of your permeability, relative permeability curves as well. So all this is important to do a good simulation. Remember, the quality of your simulation is going to be as good as the quality of the data that you have available, and it's also going to be as good as how much you understand the data that you are using as input here. Um, Obviously, if you use regions, that we will see what regions are in the case that you are not familiar. We will see them in a future exercise, but also consider that your assignment of those regions are okay, that you have properly assigned different. If you are using, for example, the characteristic curve, that the characteristic curve is associated correctly to the different regions or the different layers. Try to be consistent between using regions or using layers in your information. Something that is very common that we see quite a lot is that a lot of time you have a lot of information that is loaded that is not being actually used in the project. For example, a lot of people create regions that they don't use later, or they load all the information on the layer level and then use regions. So in this case, having that information that is not being used could be a detriment, because it could create confusion in which one is actually being used. So that is important to have it corrected as well. So as a general steps to follow, or what we will do in the next exercise, like points to follow from now on, we will generate the geometry of the injection pattern. So the first thing we need to do is to create the flow elements. Then, when the flow elements are created, the next step will be to calculate the pore volume inside those flow elements. Then we will create the injection areal distribution coefficients that will divide that injection between the different active producers next to those injectors. Then we will select our calculation model, and based on that, we will check all the data that we have. We will import more data if we need to import it, and we will create a good model based on the calculation model that we have selected. And then we will select the injection scenarios. We will also use the tool that allow us to define the injection in the for the forecast as well. And then finally we will perform the final run with our with all this information together and all the calculation methods to have a forecast using the simulation. So I understand there is a lot of information coming at the same time, but we will explain more and more each step in the following exercises. Um, I hope you are as excited as I am to start working with the simulator and do a good simulation of the project. Have a great day.